Mm-hmm. Danger Mobad. Hello. Welcome. We're doing Twitch today. The stability derivative, howdy. The stability derivative, feeling stable. Snow doesn't look as bad as I thought. People were saying there'd be like a foot of snow. Fake news. Pretty windy though, that's true. How's it going? How's everybody feeling? How's everybody doing? Happy Friday to you. We'll get started here in about a minute. Happy Friday, hello. Hello, digital controls freak. Howdy. Howdy, howdy. Question, how exactly will we be using the code we're going to be talking about today? I'll do a little refresher. at the beginning here. Talk about what this code is for, why we're doing it. Good afternoon. I guess it is technically now afternoon. What's up, Akil? We're having one midterm for MAE 444. We have a midterm and a final. Will we have the recording for today's lecture on YouTube? Yes. The answer is yes. I'll throw it up on YouTube. All right, we'll get started here. Turn this down a little. Let's see here. All right. So what we'll do is we'll bounce back and forth between the notes and our code. So you're going to want to have MATLAB open. And this is the code that we were building last time. If you're not caught up with it, if you go to our Discord, Jean-Claude was kind enough to post his MATLAB code there. And you can download that, start from there and catch up. And either way, I'll post this video to YouTube so you can come back to this and catch up. I mean, you can pause the video, compare your code line by line with this, and that's the deal. Okay, these are the notes that we were starting last time, and I'm gonna continue from here, but I want to do a quick recap. So what the heck are we building this code for? So we've mentioned that when you design a control system, it starts with some performance constraints. And the ones that we've been looking at are primarily settling time, overshoot, rise time. I think that's basically, I mean, you can kind of go from here. You can do peak time as well. Okay. So then you take this performance, which corresponds to some continuous time roots. And then because we're doing digital control systems, we're implementing this on hardware, we have to convert this to discrete time roots. And you can draw these roots in the complex plane. So you have the imaginary axis, you have the real axis. And what we're doing is we're making a code that draws in this complex plane the locations where your roots can be. And we're going to see it makes some interesting shapes. Like the first one that we did yesterday is we looked at settling time. Like if you want your settling time to be less than 2 seconds. Well, that corresponds to some discrete time roots that have to be within a circle in the complex plane. Why'd you say that we needed to convert the continuous to discrete? I think we talked about that. Okay, so because we do everything in the discrete domain, we need discrete roots. We're not satisfied with continuous roots. Okay. So this is the settling time kind of constraint. It's always going to be a circle if you want your roots to settle less than a certain amount of time. And this circle is going to get tighter the faster you want that settling time. All right. So the next one we started looking at was overshoot. And this makes a different shape. We're going to see it looks something like a heart sideways. So let's fill this in. What this would correspond to is overshoot less than something. I don't know if this would be like less than 20%, less than 30%. I'll just call it like MP star. So settling time constraints look like this. So now you can start asking questions like, what if I want my settling time to be less than something and my overshoot to be less than something? If you satisfy both of those constraints, it has to be within this overlapping region, like a Venn diagram. Okay, so that's basically to the point we got in this code. We didn't draw the overshoot yet, so we're going to do that next. And then eventually, we're going to go to rise time. So rise time, that's going to have its own interesting shape. And it kind of looks like a Pac-Man. You'll see what I mean. It has like a mouth over here. And then it like comes back around like this, something like this. So, and then you're going to have to be interior of this Pac-Man. This would correspond to like rise time less than a desired rise time. And so then you can think in terms of like, I want to satisfy rise time, overshoot, and settling time. Well, you'd have to look where all of these shapes overlap. All right. So I'll move away from here. Oh. So our strategy for drawing these contours, what determines the orientation of the overshoot and the rise time? We'll get into that. The way we're drawing these shapes is if you have a discrete time root, you can position it in the zPlane based on its magnitude and its phase angle. It's kind of like polar coordinates. For a given phase, you can determine the magnitude, and that'll place the root somewhere. So, there's a lot of details going into these things right now. I know we're kind of quickly blasting through it, but you'll see. All right, so here's the math for the overshoot condition. This is where we stopped last time. So these two lines of math right here correspond to overshoot less than some desired overshoot. And this generates a constraint where the magnitude of the roots have to be less than this over here. And I won't go back into the details of how we derive this in the interest of time. So I'm going to jump over to the code now and show where we entered in this formula. So I'm going to scroll down here. So like I said, we were starting to work on the overshoot constraint. And we made up something, an overshoot max of 20%. So we want the overshoot to be less than 20%. This corresponds to your damping ratio needs to be greater than this. So if you want your overshoot to be small, that involves increasing your damping ratio. So for 20% overshoot, that means you need a damping ratio of at least this. All right, so what I'm going to do here, I made a vector of phase angles that goes from 0 to pi. So we're going to like go around in a circle. And for each of those phase angles, I want to calculate the corresponding magnitude of the root. And that's what this is here. And that's the formula that we were just looking at on the other screen, just put into this format. So let's continue with this. I'm just looking at some notes here. Okay, yeah, so we have the magnitude, we have the phase. Now I'm going to turn this into X and Y coordinates so we can plot it. So what have we been calling this? Let's do this. I'll copy this from up here. And I'm going to change this name. I'll say, actually I'll delete this line. So this will be the X coordinate for this constraint. And essentially we're going to have the magnitude. So we'll take the magnitude of the root and we'll multiply it by cosine of the phase angle. So here we go. I'll throw this phase angle in here. So We're going around the circle, different phase angles. And then the x-coordinate is going to be the cosine of this multiplied by the magnitude of the root. Now let's get the y-coordinate as well. So now I'll just copy this. Copy pasta. The y-coordinate. And all we need to change here is that it's the sign. All right. Let's plot this. Now, I showed you last time we're using this fill command because we're filling in these like shapes. So what we're going to do, let's copy this from our previous plotting. So I'm going to copy these lines 30 through 32. And I'm going to throw them down here and kind of use the same format. But we'll call this P3. It's like our third layer here. And for the x-coordinates, we're going to put in the coordinates for this overshoot thing. Let's change the color. I'm going to do blue. And this alpha command, it makes it kind of transparent so we can see through and get that Venn diagram sort of feel. And let's append P3 to our legend. So now I'm going to put in P3 and let's put the name here. Actually, because I'm running out of room on this line, you can put a ... Press enter. And it allows you to continue on to the next line. So I'll say this is the overshoot constraint. Should we run it? It's possible that we'll get an error always when you run these codes. Let's try running it and see what it gives us. It gave me nothing. Did the same thing happen to you? You got a half heart. Let me run mine again. Wait, why is it? I had to add a dot in front of the multiplier. Oh, you're right. Thank you, guys. This is what we missed. This is what we missed, everybody. Listen, so this magnitude, this is a vector. So this has, you know, a bunch of entries because it depends on phase. Now, whenever you want to do element multiplication of vectors, you have to put a dot multiply. So add a dot in here for the x and y coordinate. You got a half heart. Let's see. Ooh, very nice. Very nice. So we have half of a heart. We have half of a heart. So to complete the bottom half, let's first talk a little bit about how this fill command works. So I'm going to go back to these notes. All right. I want to get the bottom half of the heart. I don't just want half of a heart. Okay. What the fill command does, and so we'll relate it to what we're doing right now. What we did is we made a sequence of points that goes around in this sort of heart shape. Oops. And remember, we were going from a phase angle of 0 to pi. And so we only went over to here. And so we generated these points in the top half. Each of them has a unique magnitude. The magnitude is changing with the phase. That's why we have something other than a circle. And so the fill command, it connects all of the dots like this. And then the very last dot that you provide, which is this one over here at pi, it connects it to the first one. And then it fills in that closed shape. So if we want to generate the bottom half of the heart, instead of stopping at this point right here, we have to generate more points that are symmetrical about that horizontal axis that walk back, and then we have a point that coincides with our initial point, and then it'll fill in this whole thing. So that's what we're going to do right now. I'm going to go back to, so we changed the phase angle to 2 pi. Okay, Danger Mobad, that is something that I've tried before, and I think it doesn't work if you go from 0 to 2 pi. Like if you try it, you'll get a weird shape. You won't get the half heart. And it has to do with, I don't want to get too much into this, but the phase angle for discrete time roots can only go up to pi, really, because beyond that you start to get aliasing, and it's not the shape you want. So what we're going to do is, watch this. What I'm going to do is I'm going to take our original coordinates, but I'm going to add to them. So like, let's just put these as placeholders right now. Like I'm going to take y coordinates and then y coordinates, and so this is our original set, but now we're going to add extra. So these x coordinates, they go around the circle, and then I'm going to use this interesting command that you might not have seen, flip up down. What this flip up down command does is it takes a vector and it just flips it around. So if our x coordinate is going from like -1 over to 1, then this flip up down will come back the other way. It'll go from -1 to 1. So it's kind of like we're working around the circle from the other side. And then we have to do the same thing with the y coordinate. So I'm going to flip it up and down because we're coming from the other side, but we have to make it negative so that it completes the other side of the heart. So the reasoning for this, it just goes back to that picture that I drew earlier. We drew some dots along the top half of the heart. Now we're continuing along the bottom half, and hopefully, does this work for you guys? Shouldn't we rename? You could rename them, but I'm just kind of taking it, reusing it, and taking the same variable. Let's see if it works. Aha, la 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 la, beautiful. I got an error on the legend line for some reason. Anybody else get an error on the legend? Oh, this is having data 1, data 2. Using flip up down only gave you the bottom half of a heart? So it says vectors must be same size. Do you have this little transpose on your phase? Okay, what's probably happening? Oh wait. So this is a column. This is a column. So we start with this column vector. This makes a column vector. This makes a column vector. Oh my, I think this should be, I think we need to make this into a big column. So this, instead of this comma here, I think we need a semicolon. Like we want to stack these vectors on top of each other. If you just do a column, it puts the vectors side by side. Changing that worked for you? Try putting a semicolon here. Let's see what it does. Oh, now it works for me. Okay. P1 and P2 are 1 by 1. P3 is 2 by 1. Wait, so, okay. If you're getting an error, first make sure that when you do the phase, you put this little apostrophe after it. That'll turn it into a column vector. And then when you go and build this thingy, make sure in the very middle. Oh, if yours as a slisher, if you didn't transpose this, I would just transpose it. But if you didn't transpose it, I think this would need to be a comma in here, not a semicolon. But I would just do what I'm doing to make it easier. Oh, the joys of syntax and stuff and arrays. Okay, guys, we have two shapes. So once again, the utility of having a code like this is you could say somebody it's either an assignment for this course or you're building your own control system. You're like, I need a certain settling time. I need a certain overshoot. Like, how about we go back in here and, for example, let's change this. Like, what if I want my settling time to be half a second? And what if I want my overshoot to be 30%? So I'm just changing these numbers. If I run it again, you get a different shape. And so this code allows you to like quickly recalculate, and then you can just look at this and pick some roots out of anywhere in the overlapping region, and they should satisfy your constraint. So it's a tool that'll make your life easier. Okay. Let us continue, because I want to do rise time next. That's going to create a nice Pac-Man shape on top of this. So we have to go back here to the surface. Once again, if you're having errors still in your code, don't panic. Don't panic. Keep following along with the concepts here. But you're always going to be able to come back to this video, scroll through it slowly, line by line. You're going to be all set. Okay, rise time. Remember the definition of rise time. This is saying if I generate a step response of my system like this, and it's going to some steady state value, the rise time is how much time it takes to cross through its steady state value for the first time. So it's this time right here. Okay, so typically the way our constraint's going to work is we're going to say, I want a rise time less than something. We'll call it TR star. And let's refresh the definition of the rise time. So we derived this before. Rise time is given by this formula, pi minus tangent inverse square root of 1 minus zeta squared over zeta. All right. So the rise time is a function of Well, your damping ratio and your natural frequency. And to make the rest of the math a little bit cleaner, let's call this inverse tangent term just beta. I'm just making up a filler variable. And to be clear though, let's say beta is a function of your damping ratio, because you see the damping ratio in here. So we'll just call it beta as a function of zeta. Okay, so the rise time is 1 over omega d pi minus beta, which is a function of zeta. All right. Oh, real quick. We also know that the damped natural frequency, really that's a function of your natural frequency and the damping ratio as well. So I'm substituting this expression for omega d because I want to show the natural frequency and the damping ratio in this expression. All right. So we're saying we want the rise time to be less than something. So that means this expression has to be less than some desired rise time. We'll call it TR star. All right, and then what I want to do is isolate the natural frequency by itself from this expression. So if you solve for omega n in this inequality, you're going to find that omega n needs to be greater than something. It needs to be greater than pi minus beta. You know what? I'm going to drop this function of zeta thing. I'm just keep that in mind. Beta is a function of zeta, but we'll just say pi minus beta divided by the desired rise time times square root of 1 minus zeta squared. So like the first intuitive thing here is if you want your rise time to be less than something, that means your natural frequency needs to be greater than something. So increasing your natural frequency of your system decreases your rise time. So maybe we'll put that. Increasing your natural frequency decreases your system rise time. Okay. So we're going to draw where the discrete time roots are that correspond to this. And it's a little tricky. Here's my strategy. Isn't omega n something we can't control? You have to remember, for control systems, we can control everything. No, what I mean is, for the goal of control is to redesign the system dynamics of a system. So when I talk about I want to change my natural frequency to something, I'm talking about the closed loop natural frequency, meaning the natural frequency of the system after we implement a feedback system. So this is what our natural frequency is going to be. All right. So this is what I'm going to do. If the system is underdamped, and we'll just assume that, control the world. I know, right? If the system is underdamped, we know that the damping ratio is between 0 and 1. So what I'm going to do in MATLAB is I'm going to make a vector of damping ratios between 0 and 1. Okay, that's going to be my first step. That'll be the class of all underdamped systems. And then I'm going to calculate from that the corresponding natural frequencies. So for each damping ratio that I provide, I can use this function to spit out, okay, if that's your damping ratio, your natural frequency needs to be greater than this. So maybe let's do that first. Let's go back to MATLAB. MATLAB. Oh, I was getting errors. Okay. Here we go. Okay, so I'm going to call this vector of rise times zeta tr. And I'm going to make it a vector. So we can use linspace, which generates evenly distributed points between two limits. So I'm going to go from 0 up to 0.99. I'm actually not going to go up to 1, because that could generate an error. Technically, when the damping ratio is 1, you're no longer underdamped, and that'll mess with some of the math. So we're going to go up to 0.99. Maru says, you don't get errors when you can't see the command window. That's true. They're not really there. All right, now for each of these, we have this beta variable. So I'm going to create beta. So what was beta? It was the tangent inverse of the square root of 1 minus zeta squared. Ooh, and make sure you put a dot here when you square this, because you're squaring every element in a vector. And then we're going to divide that by zeta, but we need to do a dot divide, because once again, we're dividing by every element in a vector. So dot means element-wise division. Okay. So we have zeta, we have beta. Don't you need to add 2 pi? Or are you talking about the omega? We're going to add a pi with this. So omega n, but let's call it omega n underscore tr. What does the 501 stand for? The way linspace works is it makes a vector between 0 and this number, and this just says how many points to create. So this is going to be a vector that's 501 elements long. Yep. Okay, so the natural frequency is, pi minus beta divided by, and we have to do this dot division, divided by my rise time. Oh wait, I'm gonna go in here. I'm gonna put this little double apostrophe, because we're starting a new section. This is our rise time constraint. I have to specify what our maximum rise time is. Oh wait, I was making new code in the middle of our overshoot thing. Good grief. Okay, I'm gonna cut it. I'm gonna bring it down here where it belongs. Okay. Okay, so we're gonna need our maximum rise time. So this is our constraint. The maximum rise time, I'm gonna make something up. It has to be like 0.5 seconds. Okay, so when we calculate omega n, we divide by, where is it? That rise time, tr max, times the square root of 1 minus our damping ratio squared. Okay, so be careful with all these dot divisions, with these dot powers. It has to be element-wise. All right, I'm just going to run this. It's not plotting anything, but let's see if we get an error. No errors to speak of. Okay, so that's fine. Let's go back to the notes, and then we'll go back to the code and plot this. So we generated a vector of damping ratios, and then we found, okay, for each case, the natural frequency needs to be greater than something. Actually, let's call this omega n star. For a given damping ratio, your natural frequency has to be greater than this. All right. So now what I want to do, calculate the magnitude and phase corresponding to each natural frequency damping ratio pair. So basically we made a bunch of pairs. Like each damping ratio has a certain natural frequency you have to be greater than. If you have these, that can define a continuous time root. And once you have a continuous time root, you can get your discrete time. But yeah, I want to figure out what's the magnitude and phase. And then once we have that, we can plot the shape. So here's our definition of magnitude. It's E to the minus zeta omega n times your sampling period. That's just a definition that we've gotten. And since we know omega n has to be greater than something, that's going to, actually, this is going to mean that the magnitude has to be less than e to the minus zeta omega n star times t. And let me explain why it's less than. So we know the magnitude is this exponent to a negative number, and omega n has to be greater than omega n star. So we're going to have potentially numbers that are bigger than this. So if you increase the size of this number, you're going to have a bigger number in the negative exponent, and that'll make the resulting magnitude smaller. So because omega n is greater than this, omega n star is the smallest it can be. We know that the magnitude has to be less than this. So when we're filling in our contour, we're going to fill in the side that makes the magnitude less. Okay. So next, this is magnitude. Let's talk about phase, and then we'll draw it. So this is the definition of phase. It's the damped natural frequency times your sampling period. Should we ignore the horizontal concatenation error? Arshu, I think you'll have to come back to the video and see the explanation I gave earlier on that. Okay, let's write this in terms of natural frequency and damping ratio. And this is going to result in a constraint where the phase has to be greater than So let's explain this. Because omega n needs to be greater than omega n star. This is the smallest it can be, omega n star. And if we make this number bigger, well, that'll make the phase bigger. So that's why we're going to create this like Pac-Man shape. You'll see it in a second. But the phase, so we need to fill in on this side of the Pac-Man because phase is increasing this way. All right. Let's go to MATLAB once again. Here we go. Oh, no need to apologize, Arshu. All right. What I want to do First, I want to get the damped natural frequency. So just make it a little easier. So that's omega n, which we just calculated, times the square root, and I'm doing dot times, of 1 minus zeta squared. And do the dot power again as well. All right. So we just have that damped natural frequency on hand. Let's do the magnitude of the roots corresponding to this rise time constraint. So it's going to be e, so we do an exponent, to the minus zeta times omega n times our sampling period. So we have zeta, we have omega n, so we can calculate the magnitude. Have that dot times again. And let's do the phase. So this is why I have omega d. Omega d times our sampling period. So we have the magnitude and phase for each point. Let's turn it into x and y coordinates like we've been doing. Did we define t? I'm pretty sure we did. Here it is. All right, so we're going to do, I'm going to copy this x coordinate thing from up here, because we're going to do that same style of thing again. So it's going to be the magnitude times the cosine of the phase, but we're going to do the phase corresponding to this rise time situation. And then, oh, let's change this. It should be for the rise time. And we're going to do the y coordinate. But we need the sign. Okay. First, let's grab these lines of plotting, because we can kind of recycle this each time we plot. We're going to have some more work to do with this once we do this, but so for the x and y, let's substitute in our new x and y variables. Let's make a different color. Let's do red. Okay. Before using the fill command, I want to use a regular plot command, and I'll tell you why. Because filling this shape is going to be a little more complicated. Let's call this P4 also. And for this line style, I'll just get rid of that, because I'm actually going to want to just plot a line first. I'll even get rid of this alpha, because I don't need it to be transparent. So actually, this is just plotting the x and y. We'll make a red line. But let's add something to our legend. So we'll add P4, and then I'll say it's the rise time constraint. Okay, so we're not filling yet. We're just going to plot a line. So I just want you to see this line. Can we vary the weight of the line? Says poop feast. Wow. Okay, let's pump up the line width. Good grief. Let's make it 4. Okay, do you think we'll get an error this time? No. Okay, this is great. So this is what I wanted to show you first. This shows the boundary of the roots. So at each point, like if we're doing the full constraint, the phase needs to be greater than this. So we need to paint in all of the things to the left of this. So like the way the fill command works, remember, we build these points from the origin, pushing out this way. And then if we want to fill in this full Pac-Man shape, we need to build the points that go around the circle all the way down to the other side. And then because this is going to be symmetrical, at some point over here, it's going to break off and then go back to complete this Pac-Man. So we'll need to go like all the way around. And I'm realizing we only have 2 minutes at this point. And so I don't think we're going to finish that today. So maybe Monday will be the day that we come back to this and we finish up this. But we're very close. Could you close out the plot so I can see the code really quick? Sure. Just notice my settling time constraint is a bit different than mine. That is because I went back and I adjusted my settling time just for an example. So let me scroll through this slow. Like if you came in late and you want to go back and fix this code, I'm going to post this video to YouTube so you can like go back. So we'll scroll back slowly so you could pause the video, figure out what you need. Yeah, so I changed the overshoot to 30. I changed the settling time to 0.5, so I made it a little shorter. And then we go all the way up here. So this is what we have. And like I said, once you have this code finished and we have everything colored in, this is really useful to come back to. I use this all the time when I'm endeavoring to make any digital control system. All right. I'm just going to come back over here. So that's it. Appreciate the scrolling. You're very welcome. And I'll turn on some music. So I have the MAE 334 lecture after this. Can I show the bottom part of the script again? I can. Boom. That's our rise time stuff. On your own, even if you don't want to wait until next time, it's an interesting exercise to figure out how to fill in that Pac-Man shape. Hey, good afternoon, Couch. ACP says, just curious, how are we going to make the Pac-Man shape? Are we going to define a piecewise function? Yes. There you go. That's exactly how I would do it. That's exactly how I would do it. And you can do that same sort of flip up down trick we did earlier for part of the contour. How do you leave the stream? Just close your browser, my friend. It's not rocket science. Imagine. And why would you ever want to leave? Am I staying home today so I can play Elden Ring? I actually watched a little bit of a stream yesterday. It's like Dark Souls, right? From the same people. No, I'm not at home. I'm on campus. Do I stream games? I've done some Among Us with the class. But I haven't streamed more than that. Streaming on campus, what a Chad. Chess stream. Oh my goodness. We could do some chess. But I have 3:34 in a second. So that's going to have to wait. When I get home today, will I stream Elden Ring? I don't have Elden Ring. You're working on the fish doctor? Which is the Billy Bass that can talk? I think that's so cool. Beautiful. I need my laptop charger. Bipod says, you're nice. I need approximately 50 Twitch subs to get funding for Elden Ring. The thing is, I saw IGN gave it a 10 out of 10, but is it that good? Really? Is it? The first thing I'm gonna get it to do with play Psychosocial. Some Slipknot. There you go. That Billy Bass is gonna be slamming. 7 hours in and it's fun. Nice. What distinguishes it from Dark Souls? You got a linear algebra quiz at 5 p.m. So gonna be interesting. Oh, you get a horse. Yeah, I heard the Dark Souls games are notoriously difficult. I'm just getting set up here. We got background music, some nice beats. Elden Ring is Dark Souls MMO with lore written by George R.R. Martin. Wow. The author of Song of Ice and Fire himself. Bipod says, what's the secret to a great mustache? I don't know. I don't claim to have a great mustache. I tried to grow it out real serious last year, and that is a challenge. You got to do the mustache wax thing. And even then, it was hard to tame. I respect people who can grow a nice mustache. Yeah, I think it's very genetic. Fair Enough says snow sucks. It gets old, doesn't it? It gets a little bit old. I mean, the winter sports are fun. If you can get out and snowboard and At least it's pretty to look at. Yeah. Let it free, the mustache. It was too much. When I had a long mustache, it was too much. It gets into your food. Gets everywhere. Your uncle has a Monopoly Man mustache. Respect. MP Rao going to Tennessee for spring break and it's already 70 degrees. Cannot wait. Sounds like a good time. Let's see, I want this. If you guess what I'm eating right now, you'll sub. Well, I don't have subs turned on, but I'm gonna guess exactly what you're eating. It's obvious, I know. You're eating Cap'n Crunch. Got it. Can I give bits? What's the Patreon? No, you can't give. It's all free. You're eating chicken with fried rice. Ah, dang it. That's basically what I have every day. I'm not very creative in mixing up the lunch routine. It's an honor to participate in the stream. Glad to have you here. Oh yeah, we got some emotes and stuff. Why do some users have a crown? That stands for Twitch Prime. If you're an Amazon Prime user. The Uno gamer logo. Do I stream games? No. Although maybe I'll try it sometime. Is this not a Star Citizen complaints forum? You can complain. I don't know what Star Citizen is. Okay, we'll get started in a second here. We need the Computer Man meme in this stream? Oh, shoot. You're right. Try to do a rendition. T-Rex arms. Okay. How about we get started here? All right, you're getting too good at this. I'm getting better at drawing the stick figure again and again. Okay. I'm going to turn down the music a little bit here. So we can focus. Okay. So what we're going to talk about today are relays primarily. And if we have enough time, we'll also talk about transistors as electrical switches. And this is the topic of... Oh, is this the next class now? Yes, this is the next class. This is the topic of your workshop next week. I'm putting up the documentation as soon as I can, but it'll be this weekend. Not everything, a lot of what this next workshop involves your kit, but it's also going to use a component in the lab. Hey, peace, Arshu. See you later. Okay, so here's the point of this. An Arduino, or whatever, your Uno, so on, outputs a very small amount of power. So like in the first couple workshops, we've been turning on and off LEDs. But what if you want to, I think like the BattleBots competition is this week, is that right? What if you want to control a powerful motor? Or a solenoid that takes a certain amount of voltage. The Arduino is not going to have enough power to interface with larger devices. So on its own, it can't power larger devices. So we need a way to control larger motors, etc. A relay is going to allow us to do this. Or a transistor, but we'll start with a relay. A relay allows an Arduino to interface with an external power source. And I'll put like in parentheses high power. I mean, it doesn't have to be a ton, but something that is more power than an Arduino. A relay allows an Arduino to interface with an external power source and direct that power to a larger device. All right. So a relay is kind of the interface between the Arduino and a higher power circuit. Let me show you. You actually have a relay in your kit. Let's go over here. I want to show you this. If you open up your kit, this is the relay. But I'll talk about this in a second. You don't want to just use this on its own. You need a diode, which you also have a diode in your kit, which looks like this. Kind of looks like a resistor a little bit, but on the end, it has this gray stripe, which indicates the directionality of this. But really, these two have to work together. And in the kit, it's annoying to hook these two together. So that's why when you come to lab next week, we're going to have a relay module, which looks like this. So you see it's got the relay on it, but it has this additional circuitry, including a diode, which makes it safe to use and it's easier to connect up some leads. Because if you want to use this one, if you want to connect stuff to this relay, it has these 5 pins on the bottom, which you can either solder to these or you can try to plug them into a breadboard. But the problem is the spacing of these pins is such that they don't fit nicely into the breadboard. The spacing is inconsistent. So using the relay in your kit, it's really impractical unless you solder stuff to it. And we're just taking the easy way out, and we have a relay module. Okay, so let's talk about how this thing works. So we'll draw a little diagram here. What is a relay? How does it work? Okay, so here we go. What I'm going to do is I'm going to make a high power source over here, and I'm just going to say it's 24 volts. Oops. And then here's ground. So from up here to down here, we got 24 volts. Maybe you're powering a motor. And what we're going to do is, actually, let's put a motor over here. So I'm just going to symbolically, we'll just put a motor in a circle. And I'm going to put a broken circuit here. So the 24 volt isn't really connected to the motor yet. And then this will go back to ground. Okay, so let's put a little latch here. And when it closes, it would close this circuit. So this channel over here, we'll call it normally open. And this is going to be relevant to a relay. A relay has a normally open channel labeled on it. And I want you to imagine that this latch here is held up by a spring. So it wants to stay in this normally open position. But if we were to close it, the circuit would be closed and we would have current flowing through. And so we would be delivering high power to this motor. All right. So how do we close that latch? This is what we're going to use the Arduino for. So maybe I'll erase this really quick because I want to leave it open. Imagine if you could close it with a magnet. So what I'm going to do is I'm going to draw a coil here. Plus, minus. And this is an electromagnet. So when you run current through it, it generates a magnetic force. And it's going to pull that latch closed. Okay, so here's the beauty. You have your Arduino over here. And remember, it outputs very low power. So it can't power this motor. The motor needs 24 volts. But what our Arduino can do is it can provide enough power to turn on this magnet. So an Arduino can output 5 volts. And very little current as well. Like the Arduino maybe outputs like 25 milliamps depending, but let's say something like that. Just very low power. So the Arduino turns on this magnet. That generates a magnetic force which closes this. It allows current to flow to the motor. And then if we turn off this magnet, well, then the magnetic force goes away and this spring pulls the latch back up. And so this gives us a way of turning on and off the power to the motor. So a relay is a device that contains the switch, so that linkage with the spring, as well as the electromagnet inside. So if you're saying like, what's a relay? Where does that fit in here? It's kind of the component that contains the electromagnet and that latch. And it also has lines for the power to come in from the high power source, and it has lines for the low power source to come into the electromagnet. I have something to show you. Let's go over here. So this is the relay in your kit, right? If you take off this blue container, this is what you've got inside. And so what I want you to see is this is the electromagnet. Like most of the space in there is that coil of wire. And when you run current through it, it pulls a magnetic force downward. Now, remember the normally opened channel? That's relating to the schematic. It might be a little hard to see, but so look up here. If you zoom in at this contact, so zoom in right there, you see that there's like 3 arms here. So this middle one is connected to the high power source. So like 24 volts or something. This bottom arm is the normally open path, NO. And right now you can see that those two are connected together. There's like these 2 beads that got pulled together. Why are they connected? Because the electromagnet is on right now. So it's pulling down and it connects these two, and now current can flow between these 2 arms, and then it like goes off the page into the motor or whatever high power thing. All right, so what I want to do right now is connect up. Let's connect up our relay and turn it off and on. Let's see here. So I kind of had this ready to go in advance, hopefully. So we got the Arduino. And here I've connected some stuff up to the relay module. So here on the left-hand side, essentially think of this as the low power from the Arduino providing 5 volts to turn this magnet on and off. And when it closes the contacts together, you can actually hear it. Let's see. So I'm going to plug this in. I'm just plugging in this Arduino into my USB port on my laptop. Let's get the microphone close. Uh-oh, I unplugged something. Let's plug it back in. Can you hear it clicking? So what's happening is, this is basically like the same code for the blinking LED. I'm just sending 5 volts of power here. It's turning on the electromagnet, and the clicking sound you're hearing is the switch closing to provide power. Okay, so what do we want to provide power to today? We're gonna do this little motor that's in your kit. So I'll leave that like clicking off to the side. So yeah, here's a brushed DC motor. We won't get too much into DC motors today. But this, we want to drive with a high power source. Well, not really high power, but in your kit, you have a 9-volt battery. And the 9-volt battery, oh geez. Got these wires tangled up here. Aha, okay. When the light is on, does that mean that it's closed? Yes. So when you see a light on the relay, it means that the contact is closed, power is flowing, potentially. Well, right now, So the power comes in on the other side of the relay, and I don't even have it connected. So all that's happening is the electromagnet is closing, and it would allow power to flow from these. Okay, so we're going to have the 9 volt go to this power module. This is also in your kit. So what this does is it takes this 9 volt voltage source and it regulates it down to 5 volts. So it's not really going to be 9 volts that we're delivering to this motor. We're first sending it to this power module that converts it to 5 volts. And you see in the breadboard, maybe I'll zoom in here. It's a little blurry, but you see this 5 volts right here. And this plugs into the breadboard. And so this whole column with the positive, there's going to be 5 volts running down this channel. And so this is going to be like our external power. It's in that column. We're going to use that. So let me unplug this really fast. Let me show you this circuit. Okay, I'm going to take, maybe I need to zoom out here a little bit. Let's get this battery out of the way. So I'm going to take this 5 volt column and I'm going to send it into the relay first. So I'm going to take one of these. Actually, we should take the middle one, and on here, it's going to be hard to see. It says COM. Don't worry about it. But we'll take that middle one, connect it to the high power. So it's in that same column. And then, so this channel, this is going to flow power to the motor as long as the circuit is closed. So I have the motor here. I got the positive lead plugged into the breadboard on column 25. Let's get in here. So I'm going to take this power output from the relay and also plug it into that same row. Okay, so now power goes from here over to the red. But what the heck is this little piece in between? Like, this is also in that same column. This is a diode. The reason I have a diode here is when you turn on a motor, this acts like an inductor. And what I mean by that is there's a magnetic field that's generated in here. When you turn off the motor, that magnetic field needs to dissipate. And so like we're going to be turning on and off this relay. So we're going to be turning on the motor, building up a magnetic field, and then when we turn off the motor, the current running through the motor abruptly drops to 0 because the circuit gets disconnected. There's no current flowing. Well, when you abruptly disconnect the current to a magnetic field, it generates a big voltage spike. It can create sparks and stuff. And a diode essentially prevents that from happening. So this, it has, you could call it a flyback diode because instead of the voltage spike occurring, current just loops through the motor, through the diode, and it kind of goes in this loop until the energy dissipates. I have some notes on that get into more detail that I'll post. But all we need to know for now is like this diode is here to just help us with any voltage spikes. All right, so we got the ground of the motor, and then this ground is going into this green cable, and that just goes back to the ground for the power supply. So it's just negative over here. So what we're going to do, we got the relay over here, we got the power supply. I'm going to hook up my Arduino. So you're going to hear it clicking again. Okay, so the relay is going on and off. And the power supply, it's not engaged until you press this button right here. Ooh. So you see when the light on the relay turns on, power's being delivered to the motor, and then when it turns off, the power is dissipated. So this is the main idea. Like, the Arduino can't provide the power that's generating this right now, but this power supply over here can. So the relay is like the middleman that allows the Arduino over here to send these commands that turn it off and on. Okay, so I'll turn this off real quick. Now the cool thing, even though this relay is pretty small, flip it over. How are we getting more power if it's being regulated down to 5 volts? Okay, I see what you're saying. So the Arduino outputs 5 volts, right? And so you're saying, like, what's the difference? If the Arduino can produce 5 volts and I have this power supply that does 5 volts, why do I care if it's the Arduino or this? Okay, so the answer to that is not all 5 volts is equal. So what I mean by that is the Arduino has 5 volts, but it produces a very small amount of current. This power source is also 5 volts, but it can produce much more current. And power is voltage multiplied with current. So if you have V times I, for the Arduino, it's very small power. But if you have V times I for this, it can generate much more current and it's much more power. Great question, great question. So if you look at this, it'll keep focusing in and out. But like the specs on this, it can run up to 10 amps through it. 30 volts DC, 250 volts AC. So like you'll find videos on YouTube of people powering some relatively high power stuff. Like you could have a wall outlet running power through this. And so even this little device, you can run a lot of current through here. And so even though I'm interfacing over here with just like a 9-volt battery regulated down to 5 volts, you could run something much more powerful even with this. But they make beefier relays. Okay. So that's the gist of relays. Now I want to show you a transistor. Let's grab one from over here. So let's move this aside really quick. So the same thing, just in case someone doesn't have a diode, you don't necessarily need one when the switching element is a relay. And you absolutely need one if you're using a transistor or other silicone switches. Well, I think you don't necessarily need one when the switching element is a relay. I think it's good practice to have a diode with a relay because the electromagnet in there, I mean, it's an inductor, and you're going to run into that problem of inductive kickback, just like you would for a motor. When you disconnect that electromagnet, it creates a voltage spike. So like I was showing you that picture earlier, there's a coil in here. You turn that on and off. When you abruptly stop current from flowing through that electromagnet, it creates a spike, and that can damage your Arduino. So I think you always want a diode, even on that low power side, where the Arduino interacts with this relay. I mean, it's not for sure going to break your Arduino, but I think it's just good practice. Okay. So the same thing, this is a mechanical switch. It's actually physically closing a latch. This is an NPN transistor, and you have 2 of these in your kit. And this can function this can also act as a switch. But it's not like a mechanical switch where it's closing a latch physically. This is kind of a chemical process, if you will. So you see there's 3 legs on here. One of them is you call it the collector. The middle one is the base, and the other one's the emitter. I wonder which, wait. The emitter, yeah. The way, and you also see there's like this crescent shape on it so that you can kind of figure out which side is which, because it's important, the difference between these 2 outer legs. One is the emitter and one is the collector. So the emitter is, I guess from this perspective, it's this top leg. So the high power we want to run from the collector to the emitter. So I guess following this path. But this path is normally open, meaning current isn't flowing from this leg to the other leg. So the way you open this switch is if you apply a little bit of current to the base, so this middle one. And so from the Arduino, we're going to apply a little bit of power to the middle leg, and that'll allow high power to flow from this side to this side. So essentially, you're going to have like your battery connected over here, and you're going to have your, well, your motor can be in series with it. But power is only going to flow along that channel if you engage that middle there. Okay, so maybe we'll draw a little schematic like we did for the relay. All right, let's go back over here. Okay. Go over here. Okay. So we're going to make a new drawing here. So let's put plus 24 volts here. And then we'll put, the ground over here. So it's 24 volts relative to here. And we want to run a motor once again. So I'm going to put the motor right here. So this is our motor. But I'm not going to complete this circuit. So current is not going to run through here until these lines are connected. So in here, this is where we're going to put our transistor. So this is where the switch is going to be. And so there's an electrical symbol that we use for these switches, transistors, I mean. So we're going to have this go in a little bit, and then it's going to kind of jut off to the side, jut back, and then go this way. And right here, we're going to put like a thick bar, and then this will come off to the side. So this is the transistor symbol. Actually, it's not complete yet. You draw a little arrow here, and it's pointing out from that juncture. And if that arrow's pointing out of this, that indicates it's an NPN transistor. And we won't get into the details of that so much, but basically it's a semiconductor, and the N and the P, they stand for the different doping that's in the silicone. Like you could think of N as negative, P as positive. But right now we're just focusing on the functionality. So I said there was a collector, base, and emitter. And so this one is the collector. So this leg, there's like 3 legs going in. So C for collector. This E for emitter. And then over here, B for base. And like I said, you can think of this switch as open. Like current does not want to flow from the connector to the emitter unless you provide it a little bit of current through the base. So if the base isn't connected to anything, effectively this switch is open. There's no power flowing through. All right, so we're going to have our Arduino over here. And it's going to be delivering 5 volts to the base. Now, there's always going to be a resistor that we put in here. Let's call it R. And the reason we put a resistor here is we want to carefully control the amount of current that we send into the base. Let's call it IB. So let's see. Essentially, so this is why we want to be careful about how much current we send in there. So if you send current into the base, like I said, that will open this switch and allow a certain amount of current to go through. Let's label some other currents here. So up here, let's say this is the current going into the collector. And then out of here, let's say this is the current going out of the emitter. And these should be pretty close to each other. The current going into the collector and out through the emitter. So a transistor amplifies the current flowing into the base. And so you can have an equation that describes this amplification. So take a step back really quick. So we have 24 volts up here. We got this motor that we want to power. And the current that's flowing through this is the collector current. So here's what I mean by amplification. The collector current is going to be some constant, let's call it beta. Beta is the typical value or symbol, times the base current. Depending on the transistor you use, this amplification changes. For the transistor in your kit, beta is somewhere between 100 and 300. And it changes too. Like for the same transistor, it can be different depending on how much current you're providing. So it's actually hard to say how much the amplification is sometimes, but it's going to be like somewhere between 100 and 300. So like just for example, if you provide, let's see, what's a good one? What do I want to do? Okay, this is how we'll do it. So if you hook up the motor to a power supply, and if you measure how much current runs through that motor at full power, for our motor in the kit, we want like 100 milliamps. Something like that. Maybe 110. So a tenth of an amp. And that'll spin the motor up to a good speed. So you know that's what I want my collector current to be, because that's what's running through the motor. So then you can say, okay, how much do I want to come into the base, knowing that that amplification is going to happen? So you can say IB is IC divided by beta. So like if it's 100 milliamps, so that's 0.1 amps, and I divide that by 100, what is that, 0.001 amps? I'm always bad with this math on the fly, even though it's basic. Okay, so if I only want this much current to flow through, we can kind of make sure we get the right current by dialing in this resistor. So let me show you what I mean. If you follow this path, starting from the Arduino, we start at 5 volts here, and then we're going to lose some voltage across the resistor, and then we're going to lose some voltage as we travel from the base to the emitter. Now, it's kind of standard to lose 0.6 volts from the base to the emitter. That's just kind of standard for diodes, transistors. And then we go down to ground, 0 volts. So if we do Kirchhoff's rule along that, we can figure out what this resistor would need to be to make the current 0.001 amps, or like 1 milliamp. Okay, so we do 5 volts, and then we lose voltage across that resistor, so we use Ohm's law. So the voltage we lose is the resistance times the current flowing through it, which is the base current. And then when we go from the base down to the emitter, we lose 0.6 volts because that's just like standard. And then that's 0. And here, let's solve for the resistor. Resistor, so that's going to be 5 minus 0.6 divided by IB. So, okay, 4.4 divided by 0.001. What is that? I want to like use a calculator. Okay. Good. 4.4. Thank you, Akil. 4,400 ohms. Okay. Now, what we're going to do in the workshop is I just kind of rounded this to 5 kilo ohms. So you're going to notice in your kit you have a little plastic bag, and it has a bunch of resistors in there. You're going to see a 5 kilo ohm resistor in there. So what we're going to do, we're going to output 5 volts from the Arduino. We're going to run it through a 5 kilo ohm resistor. And we chose this resistance specifically to get a certain voltage going through the collector. And that's kind of how it works. How about let's hook this up. And hopefully it works. I think it will. I believe. And I think it's cool. Like we're running this switch with this big mechanical device, and now we're going to run the same sort of thing, but with just this little guy. Okay, so let's take out the relay. We're not using it anymore. We'll just totally remove it. So we're still going to use this power supply. We still got the motor. I'm still putting a diode across the motor to reduce that inductive kickback. Let's move my laptop out of the way. So if we look at our circuit, let's zoom in here. So we have the power supply, which let's connect our 5 volts to the same column as the top of the motor here. So we're going to be running that power, but now we're going to add the transistor to be in the same column as this negative, and we want the collector to be there. So that's going to be this side. And once again, you can tell because the transistor has this crescent shape. And I'll make sure the documentation kind of shows you. Okay. So I got the negative end going into there. And then down at the bottom, so you can see it's got 3 legs. Collector, base is in the middle, and then emitter. This emitter should go back to ground. So let's put... Yeah, we got this green wire that's connected to the ground of the power supply, and it's also connected to the emitter. Now, for the base, the middle, we want to connect our 5 kilo ohm resistor, which I already grabbed from the kit. Here it is. Connected to the base, and then I'll have the other leg just somewhere out here. And then on my Arduino, let's plug this in. Let's see. Oh, just a small note, double check the pinout of your transistor. Yes, that's a very good point. The collector, emitter, and base, it's not always going to be the same. Like transistors like these are going to have 3 legs, but you always want to look up the specific data sheet to be sure which one is the emitter, which one's the collector, because that does matter. Thanks so much for throwing that in there. All right, so what I'm going to do, I'm going to grab some wires here. Pin 13 on my Uno is just turning off and on. And I'm going to connect that to this 5 kilo ohm resistor. So current's going to flow from here through the resistor into the base. And then that little bit in the base is going to effectively allow current to flow from the collector to the emitter. Okay, so I'm going to have that. I'm going to connect the ground of the Arduino to be also connected to the ground of the power supply. So it should go in this blue column. So we have the ground of the Arduino attached. We have this. Will this be recorded? Yes. Yes, it will. Okay, let's double check this circuit. Okay, I got 13 going to the base. I got the emitter connected to ground. I have 5 volts here. I have my Arduino plugged in. Oh my goodness, let's try it. Let's try. I'm going to connect. Well, I'm going to press this button on the power supply to turn it on. Uh-oh. What has happened? Let's debug. 5 volts. Oh, you know what? Let me check something. What I'm going to do real quick. So I had pin 13, which is turning off and on. What if I connect to the 5-volt pin on the Arduino? Wait, I'll turn off the power. Let's power this up again. Interesting. So what I changed is, instead of pin 13, which is going off and on, I connected it to the 5-volt pin. And this pin 13, which is going on and off, is also outputting 5 volts. But I think the default pin mode might be producing so little current that with this 5 kilo ohm resistor, maybe it doesn't have enough power to deliver the 1 milliamp that we need. But anyways, like if I connect that 5 volts to the resistor and then disconnect it, I'm effectively running a switch here. So I'm just tapping the side of the resistor and letting it go. So, I mean, the high power is on the whole time, but the switch is only closed and allowing power to flow when I connect this. So I'll make sure we figure that out in the workshop documentation. But turn that power supply off. There are no multiple current modes on the Arduino. The voltage might be lower on that pin due to it also driving the onboard LED. Drop the base resistor to something like 1K for starters. Oh, okay, because pin 13, you can see this blinking LED on the board. It also is delivering power to that LED right now. So some of the milliamps, sorry, some of the current is going here, so maybe it's not delivering enough power. Thanks for pointing that out. But that's what I wanted to show you today. This unlocks a lot of different projects, because until you start using a relay or a transistor to interface with higher power stuff, you won't have enough power to do any interesting projects. Sometimes when you don't set pin mode to output, it might not deliver the power it should. Right. That's what I was thinking of. Like when you set it to pin mode output, it does deliver more current from that pin. And that. I don't know, Lego Logan. Maybe he's right as well, or she. But that's what the workshop's about next week. I hope this is interesting to you. I want you to just see the application of these things and how we can use the Arduino to control higher power stuff. But that's basically it for today. I'm going to turn back on some tunes. I'll be hanging around for a couple minutes if people have more questions or want to chat about something. Let's see. Let's go here. Happy Friday, everybody. I hope you're doing well. Hey, Prof, I have a doubt regarding, digital controls question. What stuff can we, I'll get back to you, Akil. What stuff can we take out of our box so it's easier to pack up for lab? I'm with you. Like, I know it's a challenge. Like, the minute you open that box, you're never going to get everything back inside nicely. This week, I'm thinking of what you can take out. Like, the only other mode that delivers power is when the pull-up is active, but that won't drive an LED, not, okay. Let's go over here. So you got your kit. Well, you're not going to need this. You're not going to need this LCD thing. You don't need this stepper driver right now. You don't need this ultrasonic range sensor. Don't need the stepper motor. So like, this would save some space. Yeah. When you get this thing, it's super clean, packed up nice and tidy, and then it never gets back to that condition. Ever! Do you need to stack relays if you have a really big voltage source, or is that where the magnet spring analogy breaks down? They make relays that are beefier for driving higher power devices, but the magnet spring analogy, it's not an analogy, it's physically what's happening. It's literally an electromagnet in there that when you turn it on, it pulls a clamp shut. So yeah, they make these beefy relays. Maybe I can find one. What are some 400 level courses you would recommend or enjoy the most? I don't know which electives I should choose. Well, what are you interested in? Do you like materials? Do you like fluids? Do you like control systems? You could take MAE 444, which is digital control systems. That's what I teach that in the spring. I think it's fun. Road vehicle dynamics is good. Look at these relays. Look at see, you can see it's still a magnetic coil in there. This takes 40 amps. My favorite classes were probably solid mechanics and statics. Do you know Jason Armstrong is teaching a new like applied materials course? I would check it out. Lego Logan says, keep in mind that you want the transistor in its saturated state. That is enough current through the base that the transistor starts to act like a switch, not a linear amplifier. Take a look at the data sheet and they will have a graph that tells you what base current you need for what collector current under saturation. So no math, just a fancy lookup table. Great class. It's so great to see you back at it. Hey, thank you so much, Lego Logan. I appreciate your expertise in this and sharing your knowledge. Thank you very much. I didn't even finish my morning coffee. I'm trying to think what other materials tech electives. I'm looking at the class schedule. Oops. way, these are graduate courses. I mean, you can... Let's go to some 400 level. Advanced fluid mechanics, gas dynamics. Smart materials. Deborah Chung. She does a lot with carbon. Side. Road vehicle dynamics. Let's see, materials. Ooh, thermodynamics. Materials. Modern theory of materials. Hua. I think the class that Armstrong teaches is in the spring. Dynamic systems was also very cool. You heard 464 is good. Is 464... Yeah, manufacturing automation is good. It's got some hands-on stuff. Fair enough. If you like dynamic systems, in the spring, you can take digital control systems. In the fall, you can take continuous control systems. Where are you? This one. These are very much dynamic systems. Road vehicle dynamics, if you like dynamic systems. I wish we had more hands-on classes. I really enjoy this class's labs. I wish we did more in the machine shop. Yeah, I'm with you. I think more and more hands-on would be good. What's the difference between digital and continuous control systems? So, continuous control systems it works with linear differential equations for that particular class. And differential equations are continuous in time. And that's what the continuous control's from. I mean, that's where the continuous comes from. Digital says, hey, when we implement a control system on a computer doesn't do things continuously. It does things at discrete points in time. And so you use a different type of math to describe those processes. And so it's difference equations that we use for that. So continuous control systems is differential equations. Digital control systems is difference equations. And there's different rules for stability and stuff. But it's fun. EAS 160 hammer class was cool. I took that. And I made this hammer. Actually, I missed part of the course, and so I only made the head of the hammer. Ron, that's right. Bro. All right. I think it's time to eat some lunch. Well, it's been fun to be on Twitch again. Thank you guys. Have a great Friday. Enjoy your weekend.